Well, it's time. Welcome back, everyone. And congratulations on getting over the halfway mark for the entire course. We have 4 weeks to go, so these 4 weeks are going to proceed just in the same way as the last 4 weeks went. We'll have, when we come back on week number 6, a full week to get through. Week number 7, we'll be getting through our exam 3. Then we'll finish out Tuesday, Wednesday, Thursday, the rest of the week. On the finals week, we'll be having one day where we're just doing the last topics, 2 review days, and then Thursday we won't hold class. That'll be considered the official day for the final exam. So we're getting closer and closer to the very end. But week number 8 is where we kind of just are finalizing the course. So really 3 more big weeks that are full instructional weeks, like we're in currently. So that's essentially the plan so far. But any questions or comments at all to start us out? Okay. Well, also congratulations on getting through exam 2 if you've already taken it. I'll be grading the second exam first thing on Friday morning after getting caught up with the homework grading as well. And as far as the homeworks go, these are the 2 sections that are due today. And if you're behind on any section whatsoever, even if it was way back in chapter 2, I'm accepting any late work for full credit. It's understandable, especially since if you were, say, studying for exam 2 and you left off section 3.8, 3.9, and so on until after you complete the exam, that's a pretty decent strategy. And that's why we're really flexible as far as the due dates go and accepting late papers for full credit. But that's pretty much the entire announcement. We got it done in about 2 minutes this time. Sometimes it takes a little longer. We're starting a brand new chapter, chapter number 4, applications of the derivative. Some of them are mathematical applications. Some of them are applications to physics, engineering, and so on. Same kind of things we saw in the prior chapter. But the applications are going to be on a theme of optimization. Well, any questions or comments at all, folks, before we crack open a brand new chapter? Okay, well, let's get started. In section 4.1, the topic is maximum and minimum values, which is really quite nice in a way. This is something intuitive. We're going to be looking into a lot of graphs. And because this is applications of the derivative, we'll see what the derivative does to help us in determining maximums and minimum values. So here's how it starts. Like any good chapter in a calculus book, we need some definitions for what we intuitively know is a maximum minimum value. We still have to put it down on paper. So when we say an absolute maximum, in function notation, what we mean is it's going to be a value of the function, say f of c is the absolute maximum, but it has to be greater than f of x for all other x in D, where D is the domain of the function. So if you have a function value that just is greater than or equal to all other function values, we call that an absolute maximum. And turning it all around, if your function value f of c is less than or equal to all the other function values for x in the entire domain, then it's called an absolute minimum. So that's the whole definition, kind of short and sweet. We've seen kind of worse definitions. One thing to emphasize that's critical about the definitions are the function notation here, f of c, also where it says the value of f. When we talk about a maximum and minimum values, we mean specifically the output to the function or the second coordinate. We don't mean the full point. We don't mean the first coordinate. We're talking very, very specifically always about the second coordinate. So let's say that here and now, just to be precise, by maximum values, we mean the output f of c or the second coordinate And so we'll emphasize that as we go through the notes, exactly what we mean by when we say second coordinate is the maximum, the output of the function is the maximum. So Here's our first example. These are four different functions, because when you go to write down a function, it's not just about how you define it algebraically, it's also what you allow the domain to be. That determines the function. All the domains are different, so we have four different functions, even though they're all y equals x squared. And in each one of these situations, we want to determine the maximum minimum values of the functions if they exist. And these are pretty tricky, so we'll go through these carefully. When we're looking at this, y equals x squared, and the domain is from negative infinity to positive infinity, what it implies is the function is just going up forever in this direction, up forever in that direction. So there's no one function value that you can put there that's greater than or equal to all other f of x's. You can't put infinity here, for example. It has to be an actual real number itself. And so for as far as the absolute maximum goes, I'll abbreviate that to ABS. Max as a shorthand. For the absolute maximum on this one, it is none. There's no maximum for a function that's constantly always increasing as you move to the far right or the far left on its domain. But the good news is it does have an absolute minimum. As you move towards the origin, you take on a minimum value, 0. So we'll say that the absolute minimum is 0 itself. That's the second coordinate, but that's a hard one to see because the coordinates at that point where the red dot is 0, 0. So we'll emphasize this comment on some of the other ones where the max occurs. But that's the minimum on the first one. So that's one down, three more to go through. This is the typical function, x squared, where the domain is all real numbers. But nothing prevents us from taking a function like this one and making a closed interval be its domain. So here's the closed interval, domain, bracket 0, 2 with a bracket. Let's emphasize that that's what we mean when we say closed interval. Closed just means it contains its endpoints and all values within it. If you have a closed interval, then there is a maximum. Here it is. So we can say absolute max. Note it's not 2. 2 is the input that takes us to the absolute max. The maximum is the value of the function, but when we say value of the function, we mean the second coordinate, or the output, what f of c equals. So plug in 2 into the squaring function, we get up to here, height 4, and that's the maximum for this function. If we say 2, we could lose credit. If we say 2, 4, we might lose a little bit of credit, but not as major. What is major is we have to say specifically the 4 is the maximum of the function. So that one's not so bad. It has the same minimum. The absolute minimum we have at the lowest height, height 0. So absolute min, still 0 on this one. Well, any questions at all, folks, with the closed interval version? Okay, then the next interval gets a little bit weirder. It's open on the left end, so half open, closed on the right end, so half open, half closed. Where it's closed, we have the solid dot. We're used to seeing that based off all our graph work in chapter 2. Where the domain is missing a 0, it causes a hole in the graph right there, and so we lose continuity from the right at that point. We do have continuity from the left at this point, and we still have the same absolute maximum. The absolute max is still at height 4. So we can say absolute max 4 on this function. As far as the absolute minimum goes, this gets a little bit weird. Turns out the absolute minimum is none. And that deserves an exclamation mark because it's pretty weird when you see this sometimes for the first time. The absolute minimum isn't 0 at all because 0 is not part of the range of this function. If 0 isn't in the domain, you can't plug in a 0 and get a value f of 0 equals 0 on this whatsoever. So if it's not 0, it can't be any other number because, again, this has a weird issue when you have a half open interval here. It means we don't have any minimum that could occur at that spot. So absolute minimum is pretty weird on this one. Any thoughts or comments so far with that minimum not existing? Okay, and just to think about it a little bit more, because it is a pretty weird function with a half open, half closed interval, let's define it here, f of x equals x squared. Give it the proper domain, 0 less than x, but less than or equals to 2. That's just the same domain in inequality notation. If that's our function, there's truly an open circle right there where it's undefined, matching the same graph we have on the right. We're trying to find a minimum. One thought is you could try to put in, say, f at 0.1, but that's not the minimum because we can find values that are going to be even smaller than that. So if that was the minimum, then every other function value is going to be larger than 0.1. If I put in 0.01, we have a smaller value, but it's also not the minimum because this game can be played forever. You can get closer and closer to 0 as you would like from the right. And the limit of the function is 0, but when we talk about maximums and minimums, we don't mean the limit of the function any longer. We can get as close to 0 as we'd like and make the outputs as small as you would ever like. It just gets smaller and smaller and smaller, but it never settles down on one number, and we can always find a value smaller than that. So that's why there's no minimum whatsoever on this one. It's a pretty weird function, and the same kind of game can be played on this one on both the lower end and the upper end. If your interval looks like this, now it's a fully open interval, and open intervals are very, very weird. You can get higher and higher and higher here, but you'll never hit a height of 4. That's not a valid output to this function because 2 is not in the domain. That means as far as the absolute max goes, it's none on this one. And for the same reason, as we saw in the prior example, same issue with that lower bound, we have the absolute minimum is also none for this one. So when we put in just an open interval, as opposed to a closed interval, very strange things happen with our maximums and minimums. You can come up with a function, even a really simple one like x squared, that has absolutely no maximum, no minimum, and not because it's doing something like this. This is not the reason it has no maximum. It's even weirder. It's just some strange topology problem right now. Well, any questions at all, folks? Looking into this first examination of maxes and mins? Okay, so this is our first look at what we mean by extreme values, maximum or minimum values. I think this is the more straightforward way to look into them, absolute maxes, absolute minimums. But there's another notion of maxes and mins, local maximums and local minimums. And here's where the definitions get kind of tricky because now we have layers of meaning when we say max versus min. So keep this picture in mind when we say absolute max, absolute minimum. And here's where it does get a little bit more technical. Two more definitions for max and min, but now there's a little bit more going on with these. So we'll read these definitions carefully and apply them to this example 2 down below. So we have, to start off, C is some real number in the domain of our function. By the way, the function here, now that we mentioned domain, the domain is going to be, notice it's undefined at 0, so it's half open. We have a function value all the way to the right here. This is at 7. So we have another half open, half closed domain. So let C be any number in a domain, say for this version here, that's the domain. If there exists an open interval, AB, containing the number C in the domain, such that f of C is larger than all other f of x's in that same interval, this is for all x in that open interval AB, that will then mean f of C is a local maximum value of f. That's a technical definition, so again, we're going to look at it really carefully as we investigate this example 2 down below. Essentially, when we say an open interval AB, we're talking local now. We just want to be around the number C, where if you're really close to C, in a neighborhood of C, nearby, that function value beats everything else. It's greater than or equal to all of their f of x's. In that case, we say we have a local maximum value. And same story in part 2, just local minimum. If we have an open interval, if there exists an open interval AB, let me highlight in the same way, containing the number C such that f of C is now smaller than f of x's, not for all x in the domain, but for all x in that particular interval that we're concerned about. And let me make sure I highlight that in the same way. Just looks better that way. Okay, for all x in that same interval AB, then we'll say we have a local minimum value for the function. So that's what's going on for local maximums, local minimum values. But there's a one big consequence immediately to this definition. If you're trying to fit an open interval around a number, say around 7, but it has to fit in the domain, you have a problem right when you're at the endpoint. So let's make a statement here. We cannot fit an open interval around 7, the upper bound of the domain, and have it contained in the domain 0, 7. Turns out that's impossible, because if you want an open interval that contains 7, it has to go beyond 7. But once it's gone beyond 7, it's shot past the domain. So that's a weird technical issue with open intervals and closed intervals. And it has immediate consequence up here, which only occurs for local minimums and maximums, not absolute. Let's say it here, local min max values never, that's always a strong word in mathematics, so let's emphasize it by underlining it. Local minimum values, maximum values never occur at the boundary of the domain. That's impossible by the particular way we've defined what we mean by local maximum, local minimum. Absolute maximums and absolute minimums can occur. For example, here they are. That's an absolute max. That's an absolute min. It's occurring on the boundary of the domain, 0 to 0, 2 giving the 4 for absolute max. When you say local maximums and local minimums, it's this part that causes the trouble. If you have a local max, local minimum, you must fit an open interval around the value input where that occurs, and those values have to exist in the domain f of x for all values in that open interval. So that's the technical stuff out of the way. We'll work through local maximums, minimums, and the technicalities as they occur through the example 2 to see how all this stuff works for local maximums and minimums. But any questions so far about this new set of definitions? Now I noticed one weird typo in my example too that I guess I've never noticed before. This is a function called y equals g of x, and the instructions say find the absolute and local maximum and minimum values of f. I'm pretty sure that was supposed to mean g, so sorry for not spotting that. Let's make a quick edit here right out in the field, and now let's work on g. We want both absolute and local maximum and minimum values. And so I'll use the same kind of shorthands as we used in the last one. When we say local maximum, I'll often just abbreviate it to LOC for local, max for maximum. And likewise, when we say local minimum, I'll often abbreviate that to LOC for local, min for minimum. The best way to tackle this function is just go left to right across the domain. And the first problem point at the domain, right at 0, has nothing occurring whatsoever. It gets higher and higher and higher, and the limit of this function as we go towards the left, approaching 0, would be 5, but that doesn't make 5 a maximum or minimum value because you have to actually have an output of 5 right here. Function is defined at 0, and so at 0, there's no extreme value. So that means we're just finding all the absolute and local extreme values, minimum and maximums. We just skip to the next point. So nothing happening at 0. At 1, it's purely decreasing. So there's no local mins, maximums, absolute mins or maximums. But at 2, something definitely interesting is going on. Let me fill in the rest of these numbers here. At 2, something interesting occurs. Right around 2, there's a function value at height 2. And that's the lowest function value nearby. Not always, because at 4, it's even lower. But if we're nearby, say on an open interval that goes from about 1.5 to say about 2.5, and we really focus on that open interval, let's suppose we deleted the rest of the graph. This is all we care about if we're thinking about local minimums and maximums. At this point too, that's a minimum because it's lower than every single other point on the graph. So we can say there is a local min f at 2 equals 2. So f at 2 is just mimicking the definition here, where we say f at c for local minimum. The answer itself, we did the work, we found it's at height 2 on this graph. So the answer would be this itself, the 2. So that's what a local min looks like. And this strategy of kind of blacking out the graph is a pretty good one. If you say, cover up half the graph with your hand, another half with a page of notes in an exam 3 setting, that's a good way to analyze this function just in pieces as we go through it. So we found our first extreme value, the local minimum, because we can place an open interval AB containing the number, the inputs 2, such that for all values x in that AB, 1.5 to 2.5, f of c, which is the f of 2 equals 2, is the smallest function value. So that's how we can track through part 2 of this definition. Well, we're going to keep on moving to the right, but any last thoughts or comments on this one? Okay, let's keep on going. Next, when we move to 3, the graph is not as bad because it's a nice continuous curve through here. The discontinuity is kind of what made it tricky around 2. But at 3, it's getting higher and higher and higher. It peaks at height 4, and then turns around and decreases. It's not the highest function value at height 4, because if we look to the left, there are higher values. We got 4.5, 4.9, 4.9999, and so on. Well, if you say are locally around maybe 2.7, 3.3, here's the open interval AB highlighted in yellow, and you restrict your attention to just this region of the graph. Let's use the FBI redacted pen again. This is the only part of the graph we care about now. On that part of the graph, right around 3, that's the highest function value at height 4. So that tells us locally in this region, that is a maximum. We'll call it a local maximum. Caleb says, so there's only a local minimum if it jumps. Not all, it doesn't have to jump. So if we went back to that prior curve and just took this point here, moved it up, it would still be a local minimum, but the function value would have been at 3 instead of 2. So it doesn't have to have a jump discontinuity for a local minimum or a local maximum. The graph just happened to be tricky because it did have one in this case. Other questions at the moment? Okay, thanks for asking about that one. So yeah, the graph was continuous through here, still local minimum, but just at a different height. And now for right back at 3, we found a value right here, and we can say now that there's a local max at f of 3, the actual local max, I should go back to the original there. The actual local max is not 3, it's f of 3, which simplifies to 4 when we do the function evaluation. So locally, that's the highest value. Unless you go too far to the left of 3, too far to the right, mostly to the left, that's where the problems actually occur. But locally, nearby 3, because it has a turning point here, it goes from increasing to decreasing, we have a maximum. Well, we're definitely on our way through this. The more you practice with these, there'll be other problems or graphs to look at in the homework. The easier it is to put these definitions together. As we keep on moving to the right in the domain, it's decreasing, decreasing. It's a sharp corner, so it's not differentiable here. But differentiability so far doesn't really tell us much about maximums and minimums. The fact that it increases, though, tells us that would be a minimum value. You could call it a local minimum, and that would be just fine. But the best way to answer this one would be it's an absolute minimum. That's the lowest part on the graph altogether, right at height 1. It never reaches height 1 ever again. So we'll say that the absolute max for this function is f at 4, which becomes 1. And let me change my wording here. That's not a maximum, that was a minimum. Somehow I switched those in my mind after I started to write it. Let's double check again. We go lower and lower. We hit a minimum, the lowest part, so it's an absolute minimum. Then just starts increasing again beyond that point. So we have an absolute minimum here. This would be the answer you would have to give for full credit, saying it's absolute minimum. But just for the sake of the notes, you could also say it is a local minimum. I wouldn't dock you any points, though, if you didn't say that. I would say calling something an absolute minimum kind of wraps this information in as well. So if you left it as just absolute minimum, as f of 4 equals 1, and you didn't say that there really is a local minimum as well at this location, that wouldn't cause any harm. So we have an absolute minimum at that point. And then, like before, we're just analyzing the graph as we read it left to right. We're increasing through 5, so no extreme value around here. But as we get around here at 6, we level off. That's pretty much the same thing that happened around 3. At this location, we can put a nice finite domain that extends right around here, maybe about, looks like 5.6 and 6.4. And in that region, if those are the only values you plug into the function, if at 6, which is 3, which would go here, is greater than equal to all other function values in that domain from A to B, which we've highlighted in yellow. So locally in this region, we can say here, we have a local max, which is f at 6, equal to a height of 3. Well, we're starting to run out of values. And when we move to the right, finally here at the endpoint at 7, this one is the tricky one that has the comments that we see here in purple. This one is not an absolute minimum because there's values over here that are lower. The actual absolute minimum is a 1, and this one's at height 2, so not an absolute minimum. We might feel like it's a local minimum, but our definition says we need to fit an interval A to B around 7. But the only way we can do that is if we move to the right of 7. And where's the problem there? You have to evaluate f at x for all values in your open interval. The function values at 6.1, 6.2, and so on, they don't exist. The domain, let me try again. Domain ends at 7. So function values at 7.1, 7.2 do not exist. They have to exist to follow this definition. And so at this point 7, this is the trickiest point on the graph, there is no local min nor max at that value. Even though it looks like a local min, it's not if it's the end point of the domain, like what happens here at that dot. Well, we did it, folks. That's the full analysis on this one. Any thoughts or comments on getting through this problem so far? Okay, well, as far as chapter 4 goes, when it says the application of the derivative, the first big application we're really going for is finding ways to get absolute maxes and minimums, finding ways to get local maximums and minimums when there is no graph like this. And we'll do that using calculus. But that's the idea of chapter 4, applications of the derivative. So we'll show how to use the derivative to solve both of these problems. In fact, in these notes in section 4.1, we'll see how to get the absolute minimums and absolute maximums. Local minimums, local maximums take a little bit more work, so we'll be doing those in section 4.3. But maybe one more takeaway, now that we're looking at these. Let me put in a screenshot here so this diagram doesn't get too busy. Let's add just a little bit more information before we take a look at Fermat's theorem down below. So there's some interesting things happening with the derivative on this. We have a local minimum, f at 2 outputs to 2, right at this spot right here. At this spot, the derivative does not exist. F prime at 2 does not exist. The reason for that is, if the derivative does exist, it implies continuity. So the moment you have something that's discontinuous, these are the problems we're doing in section 2.8, discontinuity implies non-differentiability. Then we had a maximum here at f of 3. Something interesting happens here. That's a horizontal tangent line right at that spot. But if there's a horizontal tangent line, that implies f prime at 3 is 0. So that's interesting. We have a local minimum, local maximum, where the derivative did not exist or the derivative was 0. Continue to the right, there's a corner here, or sometimes we called it a cusp. At that case, the derivative also does not exist. F prime at 4 does not exist, but it led to a local minimum regardless. And as we increase through here at 6, this one had a local maximum. And here, that's a horizontal tangent line. So that would mean f prime at 6 is 0. This is essentially the insight of Fermat's theorem. When we go to investigate functions that look like this, we can say if f has a local maximum or minimum value at some number c, and if f prime at c does exist, we expect it to be 0. That's what we were observing. Every time the derivative did exist and we had a local max, local minimum, it output to 0. So the other part of finding local minimums and maximums are, we should also investigate where the derivative did not exist, because those points led to here, a local minimum, and here, another local minimum. So this becomes an important key to our analysis. If we're trying to optimize a function, find maximum, minimum values, first critical thing we're going to look at is whenever the derivative goes to 0, that's our first spot to look. Well, just because the derivative equals 0, sadly, is also not a guarantee that you have a local max, local minimum, absolute maximum, nor absolute minimum whatsoever. It's just the place to start looking. So that's what's going on with this function here. F of x equals x to the power of 5/3 is a pretty bizarre function. If you differentiate it, power rule says that this is 5/3, x to the power of 2/3. If you go to solve this equation, f prime of x equals 0, that would just imply 5/3, x to the power of 2/3 equals 0. So here's that equation. Here's what it looks like for our particular example. Because we're looking at only real value solutions, the solution here is x equals 0. But just because we found a value, 0, doesn't mean we can plug it into the function and get an absolute maximum nor absolute minimum. It really just depends on the function. So for the question of does f have a local maximum or minimum at x equals 0, we get pretty excited whenever the derivative comes out to a 0. That reminds us of a horizontal tangent line, but doesn't necessarily mean min or max. Let's look at the graph for this one. The graph for this particular function goes, it's 5/3, x to the power 2/3. Excuse me, that's the derivative. Let me try again. F of x is x to the power of 5/3. There, that's our actual function. The derivative is even weirder, it turns out. And here's our function. Let's zoom in on it just a little bit. The question is, does f have a local minimum or maximum? And the answer to that is no. It keeps on increasing, slower and slower as we get closer and closer to 0. And right here, the tangent line is truly horizontal. If this was something that's moving with time, the object is at rest right at this spot where the derivative is 0. But then it keeps on increasing when we go beyond 0. And so there's no minimum here, there's no maximum here. It just happened to have a horizontal tangent line, giving us the derivative 0. So we're going to come back to this graph because a lot of our techniques for optimization start off with the instructions, solve f prime of a number equals 0. Then we'll have a first derivative test, we'll have a second derivative test that has a whole bunch of extra steps. The reason we do all those extra steps is because of graphs like these. Just because the derivative is 0 doesn't mean you have a maximum or minimum whatsoever. And so there's more analysis to do for these kind of curves. What's mentioned here is the conclusion of this problem. Although f prime at 0 really is 0 for this function, there is no max nor min at x equals 0. The geometry of the function was just weird, so it was a false alarm, essentially, when that came up. Well, so far, Fermat's theorem is still useful. It's a starting point to look. It's not all of the places you'd want to look, because notice on the last problem, we found local minimums, maximums, where the derivative didn't exist, or just minimums, it looks like, where the derivative just didn't exist at all. So if we want to find minimums and maximums, local or absolute, we first find out where the derivative is 0, find out where the derivative does not exist. And those ideas are so important, it gets wrapped around this new definition for a critical number. The short definition of this says, a critical number of a function f is some number c in the domain of that function, such that either the derivative is 0, which means horizontal tangent line, there might be a minimum or a maximum, or Maybe the derivative just does not exist, like we saw on example number 2. Maybe there's a removable discontinuity, or maybe there's a cusp, like on that particular graph, or even a jump discontinuity. In either case, if we're trying to find maximum or minimum values, these are the first places we should look. And this theorem says if f has a local maximum or minimum at C, then we call C a critical number of f. That doesn't really say too much more beyond what the definition said originally. But again, this is pretty much our first step in our analysis for optimization. So we're going to practice finding critical numbers for these functions down below. Then we'll look into how to find absolute maximums, absolute minimums for a particular kind of functions. Well, any questions first, folks, with the critical number definition? Okay, well, let's give this a start. Example 3 says find all critical numbers of the given function. And it's a pretty fast process. If you're just finding critical numbers, step 1 is to do the following. We just differentiate the function. So that's chapter 3, working really hard for us. We took lots of derivatives. This one's a little bit trickier than a standard one because it's going to involve a product rule. So we have a first factor and a second factor. But with all the practice we've done so far in chapter 3, this should feel kind of routine at this point. Still, we'll practice these carefully since every product rule problem feels a little bit different than the other. We first differentiate x cubed to get 3x squared. We copy the second factor, natural log x. We'll plus copy the first factor, x cubed. Then differentiate natural log x. That'll be times 1 over x. And instructions when we were in chapter 3 doing these derivatives was always to simplify. Here's where it really, really matters, it turns out. Because we're going to look for where the derivative doesn't exist, or where the derivative equals 0, simplifying our function as much as feasibly possible becomes massively critical. So we'll never be satisfied with this. We'll keep on going. Copy 3x squared. Natural log x, x cubed times 1 over x is just x squared, so it goes plus x squared. And in this context, that's still not fully simplified. If we're going to solve equations like these, we want to simplify by taking it into a fully factored form as well. Turns out that's also important. This factors by taking out the greatest common denominator, x squared. So we have f prime at x is now x squared times 3 natural log x plus 1. So in the context of optimization, that would be considered the most simplified form. So we're going to look for where the derivative is 0 or does not exist. Any questions or comments first with doing the derivative? Okay, now let's take another close look at this definition. A critical number of a function is a number C in the domain of that function. The domain is part of the story on these, so whenever we do this kind of problem, it's a good idea to say what the domain is as part of our analysis. So if we take x cubed times natural log x, there's no domain restriction on x cubed, but there is on natural log x. The domain of natural log x is 0 to infinity with an open parenthesis on the 0. So that means the domain of f is from 0 to infinity. So when we go to find critical numbers, they have to be inside that domain of the original function. So now we're looking for where the derivative is 0 or where the derivative does not exist. Here's the derivative, but that derivative exists everywhere. As long as I'm plugging in numbers that are larger than 0 in the domain, this gives us a nice defined derivative. So it failing to exist is not possible in this problem. It'll happen on the next, so we'll see what that looks like. So instead, what we'll be doing in step 2 is solving the following. Solve f prime of x equals 0. This is not too bad to solve. We've done half of the work, actually, when we simplify the derivative down to this stage. This becomes x squared times 3 natural log x plus 1 equals 0. So that's the real equation for us to solve. Now the zero product property of the real numbers takes over in solving this. If you have two things multiplying and the result is 0, whether they're numbers or algebraic expressions, the conclusion is always the same. This product resulting in 0 implies either the first factor, x squared, is 0, or the second factor, 3 times natural log x plus 1, is 0. Now we just divide and conquer. We are going to solve both of these equations. X squared equals 0 has only one real number solution. X is 0, but we need to be really careful. X is 0 is not a critical number to this function, because a critical number is in the domain of the function, and our domain excludes 0 due to the natural log. So let's make a quick comment here. 0 not in domain. It's not a critical number. I'll use the hash symbol for a shorthand on number down below right here. So we got nothing from the first equation, but that's okay because now it allows us to isolate this factor, solve this one to see if we can find a critical number there instead. Any questions so far before we solve this logarithmic equation? Okay, let's give it a try. We've solved exponential equations in section, I believe that was starting to get foggy on what section that was. I think 3.8 on exponential growth and decay. This one's a logarithmic one, so it is different, but the idea is practically completely identical. Whether it's a natural log or exponential, isolate the weird part of your equation, the natural log on this one. So subtract 1, divide by 3. Natural log x is now -1/3. Now we use properties of logarithms, which says there's a kind of cancellation we can take. But we're not taking natural log of both sides this time because there's already a logarithm there. We take the base to whatever that log is. It's base e. Then take the entire left-hand side to write it in as an exponent. Take the same base and do the same thing with the right-hand side. Right-hand side is now an exponent. So you can go from this logarithmic equation down to this exponential equation. If the exponents are the same, then you can drop the base and get the prior step. The reason we took this weird looking step is properties of logarithms says there's a cancellation like that. Same one we saw in the exponential growth and decay section, except it went something like natural log of e to the x. And this one is just reverse of that, but same type of idea. They're inverse functions, so we expect that cancellation. X equals e to the power -1/3. We need to check if that's really in the domain, but e to the power of any power whatsoever is bigger than 0, guaranteed for an exponential. So automatically is in this domain. I think this is a property we said before, e to the power a, for a being anything, is always non-negative. It's going to be positive always. So we're done at this stage. X equals e to the power -1/3 rather, is the critical. I'll often write crit, short for critical, hash for number, of f. And that's where our analysis ends. That spot right there, it could lead to a local maximum or local minimum, And this theorem says if the function has a local maximum or local minimum at C, then it will occur at the critical number. So if there's any min or max whatsoever to this, it must occur at e to the power negative 1/3. Well, let's take a look at the graph just to see what else is going on. But any questions with the calculus algebra side of the problem? Okay, so here's the graph to this problem here. If I can put it in a good spot, that should do the job. It was x cubed natural log x. Notice that the domain just naturally is what we said it was, from 0 to infinity. Back there is x cubed natural log x. That seems kind of weird. Let me go f at 0. Yeah, f at 0 is undefined like I thought. I was expecting an open circle right here. Oh, now it is an open circle. I think I was just highlighting it weird when I was clicking on the graph. So yeah, it's undefined right at 0. So our domain goes from 0 to infinity. Notice there looks like there's a local minimum. Theorem says if there is a local maximum or minimum, like we see here, at that number C, then it's a critical number. We found only one critical number, so let's put in that number, e to the power negative 1/3. It's the 0.71653, that's the critical number. And that negative number, negative 1.22, that's where the local minimum, looks like it's also an absolute minimum on this graph, would have been. So that's the graphical side of this analysis. We can't do this kind of thing if we're doing it as an exam problem. When you're learning the concept for the very first time, say as a homework problem, it's not a bad idea to grab a graphing utility to kind of connect the dots. So the dots connected are, here is the critical number, e power negative 1/3, and this is the local. And just in this particular problem, it turns out to be also an absolute minimum. So we'll try it out again. Our goal is not necessarily to find the absolute or local maximum or minimum, really just focusing on the critical number. But this is the role it plays in looking into optimization. Well, any last thoughts or questions, folks, before we try it again on part B below? Okay, well, let's try this out again. Here's our next adventure, this time for g of x. Same instructions as before, but let's carry down this definition because it's new and interesting. Mainly so we can point at it while we're solving this problem. So we have this function g of x minus 4 to power 2/3. It's an interesting function for sure. We want to find the critical number. So first thing is we need to know the domain of this function. But this is a really nice function. The domain is all real numbers to this thing. So let's just say here, domain equals r, which is, I think we've used that once or twice, our symbol for all real numbers, negative infinity to positive infinity. You can just say r if you're comfortable with that shorthand. Step one, like before, is to just differentiate the function. But this one's a chain rule problem, so this is a good review on doing this derivative. We have an inner function, x minus 4, an outer function, power 2/3. So when we go g prime at x through the chain rule, first thing that happens is 2/3 carries down. New power is 1 less, so we subtract 3/3 to get a negative 1/3. We put in x minus 4, and then we multiply by the derivative of that inner function, x minus 4. But if you were looking ahead on this and you were imagining, well, how would the chain rule really go? You might have noticed this one little shortcut. The derivative of x minus 4 just happens to be 1. So, the chain rule was important, but if you literally forgot the chain rule, no one would know and you would get the right answer. Nonetheless, always be careful with these. This only happened because it wasn't, say, 2x minus 4. If there was a 2 right here, the derivative of 2x minus 4 would have been a 2, and then that 2 absolutely does matter. But for some functions, when their derivative are 1, even if you did the chain rule mentally, saw that the derivative came out as 1, the best and fastest answer to this is just g prime of x equals 2/3 times this function. So that's our derivative. And I often said that that's a pretty good stopping point if you're simplifying this. But because we have a larger context where we're solving equations or finding where a derivative doesn't even exist in the first place, let's go a step further. Let's drop that to the denominator. This is 2 over 3 times x minus 4 to a power of positive 1/3. And the next step is just a change in notation, not as critical. I just want to rewrite it as 3 times the cube root of x minus 4. So that's the derivative in its most simplified form. Now, in the next step, we're going to find the critical numbers based off that derivative there. First thing we look into is there any conceivable way the derivative is 0? The moment you eyeball this function, the answer should be no, absolutely not. There's no way to solve that equation. Let's put it down here on the notes just for the complete algebraic explanation. G prime at x equals 0 in our problem would mean 2 over 3 times the cube root of x minus 4 is 0. And this has automatically just no solutions. There's no way to solve this. Nothing you can do algebraically will provide a solution. And the reason for that is when we go to solve an equation like this, if you have a numerator versus a denominator, but your numerator is constant and not 0, of course, then the only way to obtain 0 on the right-hand side is by making the numerator 0 itself. The reason for that is you could simplify this equation and just multiply both sides by 3 times the cube root of x minus 4, essentially clearing the denominator, or doing a halfway cross multiplication. The moment you clear the denominator, you just get 2 equals 0, and that looks even worse. That's a contradiction, absolutely. 2 is not 0, no matter how weird calculus gets. And so if there was a 2x, yeah, we would have had a solution, 2x plus 4, a different solution. But if there's no way to make the numerator specifically 0, you cannot solve g prime at x equals 0. But no solution doesn't mean no critical number. You go to the next part of the analysis and find where the derivative does not exist. In our prior problem, we had x cubed times, I think it was like 3 natural log x plus 1. You could plug in an x anywhere in that derivative, and it would always exist. It would be completely fine, as long as you stayed within the domain. But this one's different. The moment you have something like a fraction, like this one, there are problem points on this. For example, you cannot plug in a 4 whatsoever on this function, because then you divide by 0. So let's say here, g prime at 4 does not exist. Deserving an exclamation mark on this one. So a critical number can occur where the derivative fails to exist, like on this problem. So now we need a conclusion, because it doesn't exist at x equals 4. X equals 4 is the critical number of G. On both parts A and part B, we found exactly one critical number, but that doesn't have to be the case. There could be no critical numbers at all. There could be 12 of them, or 2, or 13, and so on. Any finite number of positive or 0 number could be the number of critical numbers for our function. In fact, there could be infinitely many critical numbers. But any last thoughts or comments at all, folks, getting through this problem here? Okay, well, let's take another look at the graphical analysis because we're not doing the critical numbers just for fun. We're looking for maximums and minimums. So let's see what happens on this function here. First, temporarily, let's just peek at the derivative. It's kind of interesting that the derivative failed to exist. So let's take a look at it. It was, I'll just call it y equals 2 divided by 3 times x minus 4 to the power 1/3 for the cube root. And here's the issue with this one. Right at 4, we have a vertical asymptote. And so that's the reason the derivative failed to exist right there. So that's the derivative. The function we really want to analyze, however, is that one. So here's the actual g of x function. G of x is x minus 4 to the power 2/3. And you know what? You can tell the derivative doesn't exist here either because that's a sharp corner, or I think cusp is a better way to say it for this one. Derivative doesn't exist at that spot as well, whatsoever. And the graph in green shows the derivative. That's where a vertical asymptote occurs. But if we focus on just the g function for the moment, the derivative doesn't exist at 4 due to the cusp. And it led to looks like a local minimum and also an absolute minimum as well at the same time for this one. So let's put this one down just to tie together the concepts of critical numbers and optimization. So the g prime at 4 does not exist, as what we're seeing here. And also we see that g at 4 equals 0 is the local min and absolute minimum as well for this particular graph. Well, that's critical numbers in a nutshell. We're going to do a little bit more with them on these notes after we take a look at another theorem, the closed interval theorem. But any questions or comments at all with finding these critical numbers? Okay, let's turn to the next big theorem. After this theorem, we'll look into a method for finding an absolute maximum and an absolute minimum. And this theorem, it doesn't say a whole lot, but it ties together some interesting concepts, continuity and closed intervals. It says if f is continuous on a closed interval from a to b, then the function f obtains an absolute maximum value and an absolute minimum value, f at c, f at d, at some numbers c and d in that closed interval from a to b. So again, it doesn't seem like this is too big of a deal of a theorem, but this theorem is a launching point from the closed interval method that's going to help us find absolute maximums and absolute minimums. And that's what it's giving us, an absolute minimum and an absolute maximum. Actually, there's a little bit more to this theorem. This is a major component to the fundamental theorem of calculus, which we'll see in section 5.3 when we're working on the problem of integration. Turns out, if you want to prove that theorem we're going to be using before very long, this is one of the major components. So let's study it here just to see what's going on in this example down below. It's asking for the extreme value theorem specifically, is continuity a necessary condition? In other words, do we have to have continuity on our closed interval from a to b in order to get the absolute minimum and absolute maximum? And second question is asking, is the closed interval a necessary condition? So same thought for the extreme value theorem. We tore out the fact that we had a closed interval, put parentheses around A and B. Would we always get an absolute minimum and an absolute maximum every single time? So to explore that, let's just look at a couple quick graphs to see the role that both continuity and closed intervals play. In fact, example 1 at the very top of these notes was kind of hinting at this theorem all along. First thing we'll destroy is continuity and see if we can really find an absolute minimum and an absolute maximum. So let's put down just a quick graph. I'll focus on quadrant 1. Let's say the closed interval goes from an A to a B like so. And my goal is to come up with a function that does not have a maximum, does not have a minimum, and that shows why continuity was actually necessary. Actually, I use both quadrants 1 and 4. So to do this, it has to be defined on the entire closed interval from A to B. But one thing you can do is, if you lose continuity, there's lots of things that can happen. There could be, for example, an infinite discontinuity, which we're going to put down here on the graph, according to that vertical asymptote. The function could start here at A, and then it could just increase, approaching the vertical asymptote in that kind of way. If you do that, it has no absolute maximum any longer because the function values just get higher, higher, and higher. And, well, so far that looks like an absolute minimum, but it's not the whole story, because I have to make the function be defined on the entire closed interval from A to B. So I can put down say, a point right here, and let it go lower and lower and lower. Now, this is no longer the lowest point because that one's lower. It's not the lowest point either because it heads off to negative infinity as we approach the value of this number here from the right. And to make the domain all numbers between A and B, we could just define the function to have this height right here on the vertical asymptote. But by doing all those things, this function, this has no absolute max nor minimum value whatsoever. The whole problem was continuity is missing. If we force this to be continuous, the curve has to connect in some way. It can't just run off to infinity. But the moment it connects in those ways, say going from this point to this point, that's one way it can connect. But now it has an absolute maximum here and an absolute minimum there. And there's no other way you can draw this curve to prevent the absolute max and absolute min occurring. There's always going to be one, no matter how hard you try. Continuity says you have to come back down and connect to B. So now there's another absolute max, absolute min. So that's the role continuity plays on this one. Any questions so far with the extreme value theorem, looking at the continuity side specifically? Okay, next question is, how important is it to have a closed interval? So we'll take off the closed interval to investigate that question. We're going to assume continuity this time and draw something like this. We'll go from A to B. But if we take off the closed interval, say domain this time, from parenthesis A to B, so A and B have been eliminated from the domain, now it's open. That means wherever you put the height for A, it has to be as an open circle. Wherever you put the height for B, high, low, wherever you decide to put it, maybe at the same exact height, that has to be an open circle as well. I'll put it up here to change the graph around. And now, sometimes this curve could have an absolute max, an absolute min. I'll delete this curve in a moment. If the curve does this, it has an absolute minimum down here, has an absolute maximum up here, But the extreme value theorem is saying this will happen for every single possible curve whose domain is AB. But that won't quite work if we go like this. If we make our curve just do this, for example, just a line segment, it's linear from those two open circles. Now it doesn't have a minimum and no absolute minimum because we could just keep on getting lower and lower. It does not have any absolute maximum, just like the example one we saw above. As now this has no absolute max nor minimum. So because there are some curves that have no maxes or minimums, it was necessary for the interval to be closed in order for this theorem to guarantee that there will be a max, there will be a minimum. So that's what the extreme value theorem guarantees, a maximum minimum. With just two ingredients, you must have continuity. The function must be defined on a closed interval. With those two ingredients, there will be a max and a min. There's no other way around it. So that's the extreme value theorem. We'll talk about it a little bit more when we're doing integration and how it loops in with the fundamental theorem of calculus. I think I misspelled fundamental. There's an L in that word. But any questions or comments at the moment with the extreme value theorem? Okay, well, it's a great theorem. It has a great theoretical use later on in chapter 5. It gives you an absolute maximum and an absolute minimum. They're guaranteed to exist, and the hypotheses are minimal, continuity, closed interval. So that makes it really useful. But this is one of those weird situations in mathematics that actually comes up a lot. Sometimes the most powerful theorems just tell you things exist, a maximum and a minimum. They're out there, but the theorem doesn't tell you how to find it. That's kind of rude in a way for this theorem. So that's what the next method is all about. The next method uses the extreme value theorem, loops in critical numbers, and gives you a method for actually finding the minimums and actually finding the maximums for any function that's continuous on a closed interval. So that whole method is called the closed interval method, essentially the culmination of these notes. It leads to the absolute maximum and absolute minimum values of a function. Notice it has to be defined on the closed interval from A to B. It also has to be continuous as a function. So that means we're really just using the extreme value theorem. And this is just a three-step process for finding the maxes and the minimums. We find the critical numbers for step 1. Then we just do the values of f at the endpoints. The largest values in step 1 and 2 are the maximums, and the smallest values in step 1 and 2 are the minimums. So in a certain sense, it's a pretty efficient process. So we'll try that out in example 4 to see how it goes, following these strategies verbatim. Any questions or comments with closed interval method? Okay, let's take just a brief look at the hypotheses of using this method. We have to have continuity. And here's a function, x over x squared plus 1, which in section 2.5, feels like a long time ago, we would call a rational function, which means it's indeed considered to be continuous. Rational functions are continuous on their domains. And this one has domain all real numbers because there's no way to get a 0 in, like we saw in one of those prior examples. However, we're restricting the domain on this to specifically -2 to +2. So we absolutely have continuity on that entire domain. There's no way to obtain a 0 down below. And that's also a closed interval at the same time. So we hit both criteria, both continuous on a closed interval. So we want to find the values of f at the critical numbers of the function in the open interval from A to B. That's really where we start. We need to get the critical numbers. So if we're going after critical numbers, first thing we do is compute f prime of x. So this is finding critical numbers. which means this is a good review problem in its own route, right? This is a quotient rule problem because there's no sensible way to reduce this to get out of the quotient rule. So in the derivative for the quotient rule, we start by differentiating the numerator. That comes out as a 1. Copy the denominator, x squared plus 1. Go minus in quotient rule. Now copy the numerator, just x. Multiply x against the derivative of the denominator, which is 2x. Then divide the whole thing by the denominator squared. X squared plus 1 squared. So there's the derivative. And like we mentioned before, we always go further on this. We need to simplify this as much as feasibly possible. And sometimes in chapter 3, that was like 70% of the work, trying to simplify to try to make that reasonable to look at. It's all because of what we're doing in these notes. We took all those steps simplifying and sometimes complicated functions. Our next step is just to expand the numerator. It's x squared plus 1 minus 2x squared. Divide by x squared plus 1 squared, which means we can rewrite this as 1 minus x squared over x squared plus 1 squared. In chapter 3, that was considered good enough, but in chapter 4, we have to go even beyond. We need to set this to 0, and the only way to get 0 to be solved is if the numerator becomes 0, so we need to factor in the numerator to assist in solving this equation. So the next line, f prime of x, when we factor the numerator, becomes 1 plus x times 1 minus x. That's really just a difference of squares up above. Divide by x squared plus 1 squared. So there's f prime of x. In our adventure for finding the critical numbers, the next thing we did was solve f prime of x equals 0. But solving that derivative is basically immediate. Solving f prime of x equals 0 means you're solving 1 plus x times 1 minus x equals 0. I skipped out the denominator, but if you did throw the denominator in, this is what it would look like. X squared plus 1 squared. But my immediate next step, if you did copy in the denominator, is to multiply both sides by the denominator. You're just feeding it to 0 through multiplication, which just wipes it out. So it's still 0 on the right-hand side. Left-hand side is still 1 plus x times 1 minus x. And so that's the comment that we mentioned before. That was supposed to be a comma. It looked like a multiplication symbol. If you're solving a fraction set equal to 0, the only way you ever get solutions is by taking the numerator and setting the numerator specifically equal to 0. So this has solutions. X equals -1, +1 are the critical numbers of our function f. So we're still in step 1, find the critical numbers of f. And now we want to find the values of f at the critical numbers. So now we can begin step 1. Step 2 says, find the values of f at the endpoints of the interval. Really, to do this as efficiently as possible, you would just combine both step 1s and step 2 at the same exact time. So let's do those together. There's really a step 1 officially is get the critical numbers, and then we're just doing evaluations. Well, any questions at all, folks, to hear? Just getting those critical numbers? Okay, well, let's take these values, find the values of f at the critical numbers, the values of f at the endpoints of the intervals. Here are the endpoints. This just means go f at -2, f at, I'll skip to the next critical number, -1, f at the next critical number, +1, then back to the right endpoint, f at 2. So 4 function evaluations. And notice we really have 2 functions. We have the derivative down here, but that's not what steps 1 and 2 are referring to. they're referring to the original function f. So we go back to whatever f is, do all of our function evaluations. At -2, that becomes -2 over 4 plus 1. So this is -2/5. Plug in -1 there, and we get to -1 over 1 plus 1. So this is -1/2. Plug in +1, we get 1 over 1 plus 1. So that's +1/2. Finally, plug in 2, we get 2 over 4 plus 1. And so we get 5/2. So there's all the valuations. And -2/5, that's about -0.4. -1/2 is -0.5. That's even smaller. Here's what step 3 says. The smallest of these values is the absolute minimum. So that's the absolute minimum right there. And likewise, I think I did that one backwards. That's 2/5, not 5/2. Let me revise my arithmetic there. 2/5 is 0.4, but 1/2 is 0.5. So that one's larger. This part says the largest value in step 1 and 2 is the absolute maximum. So all we need is a conclusion. We can call this the absolute maximum. And we can call this one the absolute minimum. And right at that stage, our work is done. Combining everything we know about critical numbers, and in particular, the extreme value theorem, into this method just makes kind of a short tour on getting everything we need. This is essentially step 3, stating what the values are for the absolute max, absolute minimum. Well, we did it, folks. Maybe one more word of warning. Keep in mind, we can't say -1 is the absolute minimum. We can't even say -1 comma -1/2 is the absolute minimum. I need to know that you know it's the function value. Specifically, -1/2 is the absolute minimum. And likewise, +1/2 is the absolute maximum. So make sure to emphasize the function values on your work on homework as well as on exams for these concepts. Well, that's the conclusion of maximum and minimum values. It is kind of an adventure when you put it all together like we have. Any last questions or thoughts before we take a look into the next section? Okay, well, let's crack open the next section, see what we're getting into for section 4.2, the mean value theorem. The mean value theorem section is a more theoretical section. Just like we mentioned before, this also has another component that's necessary in the fundamental theorem of calculus. It's the mean value theorem. But these ideas are kind of useful in their own right. We have 2 big theorems we're going to take a look into in section 4.2. And the first one is not even the namesake of the section. First, it's going to be Rolle's theorem, or Rolle's theorem is the typical way to say it, I think. Rolle's theorem has 3 hypotheses: continuity on the closed interval, differentiability on the open interval, and function values match at the endpoints. So if those 3 hypotheses hold, here's what Rolle's theorem tells us. There is a number, c, inside the open interval from a to b where the function is defined, such that f prime at c equals 0. And that equation, it just keeps on coming back a lot throughout these notes. Here's one way to think about what Rolle's theorem is really saying altogether. It's a set of criteria, 3 hypotheses that we'll check, that gives you this. Rolle's theorem guarantees a critical number, and it doesn't just guarantee a critical number, it actually tells you where it is. It's within the open interval. It's going to be less than B and bigger than A. It'll never be at the endpoints. So when we find the critical number for Rolle's theorem in the conclusion of Rolle's theorem, we're looking for specifically the number that's guaranteed through this theorem to be between A and B. So that's the analytical look at the theorem. It's essentially just one big guarantee. Whenever we're looking at technical theorems like these, even on the very first day of class, it's always good to kind of graph these out, to connect the dots with some mental picture of what Rolle's theorem is actually saying. We'll do the very same thing as well with the mean value theorem. So here's what the picture is for Rolle's theorem. Start off with a gigantic graph emphasizing quadrant 1. It's going to be continuous on a closed interval from A to B. So we'll start at A, end at B. Well, continuity just means we're going to draw a curve, never lift up the pen, no vertical asymptotes, jumps, removable discontinuities. It's going to be differentiable, so no corners or cusps either at the same time between on the open interval from A to B. And this one's critical. It also says when we define f of A at this height, here's f of A, it has to also be equal to f of B. So for Rolle's theorem hypotheses to be met, that dot has to be right exactly there. It can't go up, can't go down. It has to be right at that line. So we're going to connect the dots essentially from A over to B in a way that's both continuous and differentiable at the same exact time. And here's one way to do it. Can just make it kind of go up and maybe down in that kind of way. Want to make it go just slightly different. So there's our curve. So it's continuous. We don't have any discontinuities there. It's nice and smooth. There's no corners or cusps, not intended to be anyways. The height of the points at A and at B are identical. F at A is F at B. And so here's what Rolle's theorem says. There is some number C between A and B. Here's the portion that we'll emphasize, such that the derivative is 0. But we really just tie that back to the geometry of what a derivative is. The derivative is the slope of a tangent line. So if the derivative is 0, it means the tangent line must be horizontal. And the way I drew this curve, that happens at exactly one spot, right here. Here's the number C that's vertically below. Notice that C is definitely between A and B, so we meet that criterion for where C is, and go up above because the tangent line is horizontal. It is absolutely true that f prime at C is 0. In other words, we can say that is C is a critical number of f. And by the way I drew the curve, we also have an absolute maximum right at that height as well. But that's the key essence of Rolle's theorem. Any questions or comments about it so far? Okay, so it's one thing to see Rolle's theorem on paper, and another thing entirely to actually use it. So let's take a preview at the next problem. These problems are pretty similar to what you'll be doing in the homework as well. I tried to write my instructions pretty similar in a parallel way to the actual homework instructions at the same, so that it looks very familiar when you're solving the homework exercises. Here's Rolle's theorem, same statements, just a little bit more compact. And here's our particular function. F of x equals x cubed times x minus 7 power 4. And here's where sometimes a lot of the work comes into place. We have to do this on our own work as well, because if we're going to use Rolle's theorem, we have to make sure you can use it in the very first place. That's what the verification is all about. Verify our function satisfies the 3 hypotheses of Rolle's theorem on a particular interval. Ours is 0 to 7, means we have to check these things and show why they're true. Some of them go a little bit fast. So let's take a look at step one. F has to be continuous on a closed interval. We do have a closed interval, but we also have to explain why it's continuous. But that shouldn't be too bad. X cubed times x minus 7 to the power 4, that's really just a polynomial. And you can use theorem number 7 on continuity. This is all the way back in section 2.5. It told us that rational functions are continuous. We looked at that earlier. Also, polynomials are continuous. We put down a 7th degree polynomial as an example, just a random one. And this one also happens to be, if you expanded it all out, a 7th degree polynomial. But any polynomial to any degree is continuous. So we are automatically continuous on 0, 7. So here's what the work would look like on this one. F is a polynomial. And so it is continuous on 0, 7. Let's say how we know that. Really just check theorem 7 and section 2.5 is our justification. So we'll say by theorem 7 of section 2.5. So that means one hypothesis is done. Nothing further to that story. Second hypothesis, we need to check differentiability on the open interval from A to B. But it's just as fast because one key fact we know from calculus is if you take a polynomial, differentiate it, it will still be a polynomial. The degree just drops down from degree 7 to degree 6. In other words, if we took that polynomial and differentiated it, that'd be 7 times x power 6 plus 3 times x squared. It's still a polynomial. It'd be differentiable on the entire real number line. So it'd be differentiable from A to B. So for step 2, the step doesn't always work. Say, if there's a denominator, we have to double check what the domain is for that derivative. But in this case, if you get a polynomial, the derivative exists everywhere. So we can say this, f prime is a polynomial as well. And so f prime exists on, it's talking about the open interval, which would be, for our problem, 0 to 7. So there's never going to be a loss of differentiability when you have a polynomial. In fact, just as a recap, the time we saw differentiability not existing is when we came across this problem right here. That had a derivative that did not exist right at 4. It was a complicated function, and the reason it didn't exist is we could see by visual inspection the derivative will exist for all numbers except 4. It's the denominator that caused the problem. But the fact that we start with the polynomial, we differentiate it, and we still get a polynomial means the derivative will exist on 0 to 7. So step 2 is down on this one. It's going kind of quick. The last thing to take a look into is part 3. The function's outputs have to match on the boundary values. When it says f of a, our value a is the left endpoint of the domain of the function. So this would be f at 0. F at 0, that would just be 0 times 0 minus 7 to power 4, which is 0. So that's the f of a part. We now need to calculate f at b. But f at b, b is just the upper bound of the domain. That's taking f at 7. That looks nasty at first, that's 7 cubed. But then it's multiplied by 0 to power 4, plugging 7 into that position, so we still get 0. Those two function evaluations show that, yes, f of a equals f of b. And our problem, what we're showing is that f at 0 equals f at 7. So that's parts 1 through 3. We just write down a few short words justifying continuity, differentiability based off what we know of the function. This is where we do a little bit of actual mathematics where we write down some numbers, compute some stuff. If you have equality here, and steps 1 and 2 worked out, we can now say this shows F meets the hypotheses of Rolle's theorem. Let me fix that R. So that takes us to the next part where here's the conclusion. There's a guarantee of a critical number in AB, which will be between 0 and 7. That's a part where we probably can't do that in the 4 minutes and some change left over. But we'll refresh this when we come back on Wednesday night to start this off on the hypotheses and work through the conclusion part of example 1. Then we'll take a look at what's going on with the mean value theorem, slightly different hypotheses and conclusion, and really just kind of redo another one of these examples, but this time next time through the mean value theorem. Well, this will be a good stopping point for us today then, so we don't go right up to the minute or past time. Any last questions or comments at all, folks, before we call it a day? Okay, well, have a great night, everyone. When we come back next time, we'll get through these notes 4.2 and probably take an early look into section 4.3 as well on finding local minimums and local maximum values. But have a great night. I'll see you all Wednesday.